Well, thanks to the organizers for this invitation to speak. I'm Ethan Campbell. I'm a postdoc at UW at the Applied Physics Lab working with Melinda Webster. I started in January, and this talk is about a quarter of my PhD thesis over at the UW School of Oceanography. I was working there with Steve Reiser. And my goal with this talk is not only to share my research on a Lagrangian reconstruction of snow evolution on Antarctic sea ice, but also to evangelize a bit about the importance of snow on sea ice, which I think is an underappreciated player in the polar climate system. By the end of this talk, my hope is you're convinced as I am of its importance. So I love this diagram, which is from an Arctic sea ice perspective, because it shows both how the complex morphology of snow develops seasonally as well as vertically as these layers of snow get deposited and then metamorphosed. And it also highlights nicely the time dependence of these, all of these functions of snow on sea ice, which range from controlling whether snow gets pushed hydrostatically below the sea surface early in the season, leading to flooding, to controlling the surface roughness, which matters a ton for momentum transfer. So clearly sea ice is important for, snow on sea ice is important for too many reasons to list, but on the right I've taken a stab at naming my top reasons for caring about it. So first, it modulates the combined albedo of snow and sea ice. Snow is reflective, right? The albedo is 0.8 or to 0.9 compared to 0.5 to 0.7 for bare sea ice. Not to mention that when the snow melts, the albedo of melt ponds is anywhere from 0.1 to 0.5, which can really hasten melt by increasing absorption of radiation. Second, dry snow has a really low thermal conductivity, which means that it insulates the underlying sea ice. And just as an example, only 30 centimeters of snow cover over 2 meters of sea ice can cut in half the conductive heat flux that sea ice experiences. And that's actually a double-edged sword, because on the one hand, snow-covered ice grows slower and is more susceptible to melt from ocean heat fluxes. But on the other hand, snow shields ice from incoming radiation that could cause melt. And those different effects can win out at different times. Third, snow changes the optical properties of sea ice, how quickly radiation attenuates, as well as how much it scatters. And that matters for the growth of sympagic algae, or ice-associated algae. Fourth reason, recent work has shown that snow getting lofted by the wind can lead to sublimation and the release of sea salt aerosols. In the Arctic, it's thought that this nucleates a large portion of cloud formation. And of course, that has impacts for the radiative balance, radiative forcing, like indirectly. And then lastly, what I'll focus on in my work is the fact that snow deposited on sea ice effectively redistributes precipitation in time and space. So it acts as a filter that determines when and where that snow is released into the ocean. A great way to appreciate the complexity of snow on sea ice is to look at how it behaves in the Arctic, where generally speaking, you have a thicker ice cover covered by thinner snow, and compare that with the Antarctic, which has the opposite, thinner sea ice and thicker snow. And I'm showing here a 2021 paper by Marika and colleagues, which illustrates these differences, I think, really elegantly. So what they did was force CSM2 with varying amounts of snowfall from 1/4 to 1.75 times that of the control run, which are those bars shown from left to right here. And they found that the Arctic sea ice mass balance on the top is relatively insensitive to increasing snow, which they attribute to an increase in the fraction of sea ice that's perennial versus seasonal that gets compensated by a decrease of the growth rate of that perennial ice. So it's kind of complicated. In comparison, in the Antarctic, the addition of snow has a really large effect because the sea ice is so thin that snow loading leads to more flooding, and that flooded slush freezes into snow ice. So this total ice growth increases quite a bit with more snow. Ice melt also increases because there's more ice to be melted. And sea ice is mostly seasonal in the Antarctic. So that is more of a simple explanation. You know, what I would perceive as a big uncertainty here is that these changes in the Antarctic have only been explored in two coupled models, where the ocean component is either a simple slab layer or continuously restored to match observations. And that matters because both of these prevent interactive ice-ocean feedbacks, which could potentially be really important when you start thinking about how ice growth results in brine rejection and associated convective mixing and upward heat fluxes. So I think this is still really fertile ground for further research. So the amount of snow on sea ice is clearly important, certainly in the Antarctic. But we have a problem, which is that we don't really know how much snow there is. So as recently as 6 years ago, the IPCC put into writing that snow depth on sea ice is essentially unmeasured, limiting mass balance estimates and ice thickness retrievals. I think this is a bold claim that might be a bit of an overstatement, but there is some truth in it. And accurate snow depth data matters a lot because, as this diagram shows over here, and Helen alluded to yesterday, a primary way of estimating sea ice thickness from satellites is to use laser altimetry, which sees the snow surface, combined with radar altimetry, which more or less sees the interface between snow and ice. And then you use hydrostatic balance combined with the densities of snow and ice to back out that ice thickness. And as you can imagine, this procedure is really sensitive to the snow depth. It's not like we don't have any information, but the problem is that our existing estimates diverge pretty significantly. So at the top, this is for the Arctic, our reanalysis-based reconstructions of snow on sea ice. So these are models ranging from quite complex to quite simple. They're forced with reanalysis snowfall, and they incorporate some range of snow processes. And at the bottom are remote sensing retrievals, which use various combinations of radar altimetry, laser altimetry, and passive microwave radiometry to estimate the snow depth. And I should note that this paper didn't include more recent estimates that combine ICESat-2 with cryosat-2. But the bottom line is that there are clearly large discrepancies across the board, though I think some of these estimates may be closer to reality than others. That was for the Arctic. I want to put a finer point on my motivations for better constraining snow on Antarctic sea ice, where existing estimates are more limited and I would say more divergent than the Arctic. So for one, our current observations, which we'd be using for validation of satellite retrievals, mostly come from researchers observing snow and ice from ships. And this data has a known bias towards thinner ice and snow due to the nature of ship navigation, which you can see in the sort of the rightward skew of this plot that compares cryosat-2 ice thickness with the available ship observations, which I should mention are also really, quite sparse. Passive microwave radiometry from ANSER has offered daily estimates of snow depth for a while, such as this one. But these retrievals suffer from significant biases and limitations related to weather, contamination, and changes associated with snow wetness and grain size. So a natural alternative strategy is to use this, a model reconstruction forced by atmospheric reanalysis. But only 2 such reconstructions exist today for the Antarctic, one of which is pretty old, and the other of which was published last year. But in both cases, their treatment of snow is highly idealized, even more so than in most coupled climate models. And the same is the case for 2 out of the 3 existing snow reconstructions in the Arctic. So what I'll be presenting is a model that I've developed that represents a step up in complexity in representing snow processes on Antarctic sea ice, and not just including those processes, but also trying to better constrain their magnitude by calibrating the whole model to, I think, more reliable autonomous observations of snow. But before that, my last piece of motivation is that Antarctic sea ice seems to be rapidly changing, as we heard in many talks yesterday. So I won't belabor this, but overall, we think that both climate variability and heat release from the subsurface ocean have played a role. And one piece of evidence for this is the ocean warming that we've seen in the lead up to that initial sea ice drop in 2016. So somehow that subsurface heat, we think, has made it into the upper layers of the ocean, perhaps due to increased Ekman upwelling or mixing. And we know that both of those, upwelling and mixing, are highly dependent on stratification, which is of course affected by the freshwater balance of the upper ocean. So Lily's talk yesterday highlighted really nicely how stratification is important for some mesoscale processes which affect the ventilation of heat. I'm sure Earl's talk after the break will also discuss the importance of stratification. So this all brings me to snow fluxes, which together with brine rejection and ice melt are the major contributors to stratification in the Southern Ocean. And to better quantify these freshwater fluxes, I would say we need better constraints on the magnitude and the location and the timing of snow release into the ocean. You might be thinking, why is this a challenging problem? Because snow falls, it accumulates on sea ice, and then it gets released into the ocean upon ice melt. Simple. But when I think about snow processes, you have to start thinking about the mass budget of snow on sea ice, which includes a variety of mechanisms through which it can be transformed and lost. And I've listed a few here. So for one, as I alluded to earlier, snow becomes more vulnerable to sublimation when it gets lofted into the air by the wind. When that happens, one model suggests that this may remove around a quarter of snow annually from Antarctic sea ice, but this is pretty uncertain. That wind-blown snow is then easily trapped into leads, cracks in the sea ice, where it may melt into the ocean. And field observations suggest that as much as half of all snow that gets deposited, or on the other hand, almost no snow, might get trapped in leads. And then there's the conversion of snow into ice from that isostatic depression, flooding and freezing process known as snow ice conversion. And that's a process that causes significant ice loss, snow loss in the Antarctic, in contrast to the Arctic, where it's not generally that important. Then lastly, rainfall on snow events may lead to significant but uncertain amounts of melt. So what I've developed to address these uncertainties is a model that accumulates snowfall from ERA5 reanalysis along these remotely sensed Lagrangian sea ice drift trajectories. So every year the model tracks about 500,000 Lagrangian parcels, which get initialized as ice forms, they get destroyed as ice melts. So this image shows snow accumulation on every 250th sea ice parcel over 1 year of the model run. The model includes processes that are important, or I think should be important for resolving the mass budget of the snow layer, as well as changes in the bulk density of snow. So this isn't a full thermodynamic model of snow, but rather what I perceive as the essentials for mass change. And it includes a variety of loss and melt parameterizations that I'll highlight next, along with mechanical compaction of snow due to overburden pressure, and changes in the large-scale average snow depth due to sea ice convergence, which produces rafting and ridging, as well as divergence, which enables new ice formation without any snow cover, and therefore it leads to thinner average snow. And in order to conserve mass and volume of snow when that convergence or divergence of sea ice occurs, I've used a technique known as Voronoi tessellation, which creates this subdivision of polygonal regions that you can see here in this image of the Western Weddell. So each polygon represents one parcel or virtual ice flow. And this technique basically allows the model to track the changing areas of those Lagrangian parcels as they converge or diverge. And when they diverge, that's when new snow-free ice parcels are instantiated. So the way that I built this model was to search the literature for existing parameterizations of the processes shown here, to find ones that have a firm physical or theoretical basis, and specifically ones that could be forced primarily by atmospheric reanalysis. Those that ended up in the model came from field studies, from modeling and theory within a variety of contexts that includes terrestrial snow, snow on the Antarctic ice sheet, and of course snow on sea ice. This diagram includes the parameter dependencies of each of those parameterizations, which include wind transport into leads, blowing snow sublimation, surface sublimation, density compaction of new snow at high wind speeds, as well as due to gravity over time, snow melt, both in times of rain and no rain, convergence and divergence, and then a simple accounting of superimposed ice formation due to melt. And I should emphasize that the bulk density of the snow layer is prognostic, affected by wind-driven compaction, as well as that settling over time, which implicitly includes a variety of metamorphic processes. I'm happy to talk more about these parameterizations afterwards or online. I should note that I specifically chose these to strike a balance between rigorously treating these processes on the one hand, but also having them be lightweight enough to meet the lower computational requirements that might be needed if these were to be implemented into GCMs in the future. And to briefly illustrate two of the processes that I just introduced for the first time, what I'm showing on the left is a snow ice core from the Weddell Sea that it contains this 25 centimeter layer of superimposed ice. And this process, which the model tracks, occurs as meltwater from surface snowmelt percolates downwards and then freezes when it contacts the cold sea ice below. On the right is a microcat scan of a snow core from Arctic sea ice. I think it nicely shows how the snow microstructure changes due to wind compaction of fresh snowfall, which is marked as that wind compacted crust. And that process matters because it locks up older snow and it prevents it from being transported from by the wind. And here my model relies on a parameterization of the time it takes for freshly deposited snow to reach that state based on an estimate of the force required to disaggregate bonds of snow particles of a certain age. So next I'm going to share how I calibrated and validated this model. So each of these snow parameterizations represent certain relationships between, say, wind speed and blowing snow mass transport, hopefully with some accuracy. But we'd still expect them to require calibration for a few reasons, because for one, most of them weren't developed for sea ice context. They probably have biases. The input data probably has biases as well. And then, lastly, it would be ideal to somehow capture the effects of unrepresented processes that have similar parameter dependencies to those that are represented. So my solution was to include 8 free parameters in the model, which are generally multiplicative scalings on individual mass budget terms. The good news is that most of the processes in the model require pretty specific meteorological conditions that are relatively independent from each other. So the model is, I think, amenable to being constrained using the simultaneous adjustment approach. And for the calibration data, I've turned to what I think are the best available observations of snow evolution on Antarctic sea ice, these 39 snow buoys that have been deployed by AVI since around 2013. The tracks are shown here. The colors indicate snow accumulation, and this photo here just shows this simple instrument. It's basically a mast with 4 ultrasonic sensors at the top that are downwards facing that measure snow accumulation. And I've randomly partitioned those 39 buoys into a calibration set that represents 3/4 of them, 29 buoys, and then 1/4 of them, 10 buoys, are used to validate the model and produce an error estimate. So for the optimization procedure, what I've chosen is a technique known as successive halving. It's, in short, an algorithm that allocates more resources towards exploring promising regions of this 8-dimensional parameter space. And it operates by running the model along each buoy track using different randomly generated parameter sets. Then it evaluates those results against the observations and then promotes the best performing half, whose distribution determines the next batch of parameters. And this procedure is repeated until the model performance is no longer improving. The result compared against that validation set of snow buoys is an RMSE and bias that are pretty comparable to passive microwave estimates. But that's notable given that the buoy estimates the buoy measurements are point estimates, and those are affected by all sorts of lateral inhomogeneities like snow drifts. And as this example shows, the calibration is not, the model definitely isn't perfect, but it often does a good job at capturing fluctuations in snow depth, and the overall evolution over a matter of months is pretty accurate. So briefly, here's what that procedure looks like for the bias of the daily tendency of snow on sea ice, and then the 8 free parameters as they get adjusted through 12 iterations of the successive halving procedure. So we see, first of all, that the final calibrated parameters yield almost a 0 bias of the daily tendency, the daily change, indicating that the model is representing those daily fluctuations in snow pretty well. So some parameters converge to values similar to their initial guesses, but most of them, especially lead trapping over here, change significantly. So in that case, like the unscaled parameterization predicted too much lead trapping of snow, and that had to be tuned down. Notably, the rate of new snowfall ended up with a 30% increase, suggesting that ERA 5 reanalysis underestimates snowfall on Antarctic sea ice, which is consistent with results from a different Lagrangian model for Arctic sea ice, snow model LG. And I should point out that in some cases, like non-rain related melt here, the model appears to not really converge to a great answer, suggesting that the parameterization in this case, I used a degree day approach, isn't that great at constraining that particular term. As an example of how important that calibration is, I'm showing now a comparison between 1.5 years of observations from one of these snow buoys versus, and that those observations are in red here versus the model simulation in black. So first of all, this dashed black line on the top is what you get when you account for snowfall accumulation alone, so no loss processes. That's around 2 meters by the end, right, which is way higher than the buoy measurements. The model's baseline parameterization without any calibration, on the other hand, gives this dotted gray line. So after the calibration procedure, we get the black line, which shows that the model is tracking the observations better. So clearly, much of this snowfall must have been lost or transformed. And on the right, I've partitioned this into the various loss processes. I think most striking is the role of snowmelt unrelated to rain in yellow, which the model finds responsible for nearly all of that big decrease around the start of 2015 here. It estimates around 30 centimeters of superimposed ice formed as a result. And that's an interesting conclusion because around the same time, the buoy was seeing both air temperatures slightly above freezing as well as multiple rainfall events. And a previous study that examined this exact same buoy record hypothesized that both the warm air and the rainfall was probably leading to that melt. And in contrast, our model shows that that's not likely to be the case. And in this example, as well as the results that I'll show for the whole Southern Ocean, we find that rainfall simply doesn't seem to be causing much snowmelt at all. It's a sliver that is too small to see here. However, the remaining processes, these 4 slices from gray to green, all seem to be playing an important role. So now for the broader results. From running this model for 22 years, from 2003 to 2025, we get these first estimates of average annual snow mass budget terms, which show, I think, a couple interesting things that I'll walk through. So we see 1 to 2 meters of annual snowfall across the sea ice zone, which is lower in the sea ice pack interior and concentrated along the continental margin. And we find mechanical compaction is greatest in areas of either higher snowfall or thicker multi-year ice as expected because more snow equals more compaction. We find that large-scale ice divergence contributes to area-averaged snow thinning of around 20 centimeters within the Ross and Weddell gyres. And this reflects the fact that ice drift is predominantly divergent within those gyres. We find rather spatially diffuse surface sublimation with rates quite a bit lower than one previous model estimate. And then in contrast, our model shows a lot higher and more distinct pattern of strong blowing snow sublimation, especially along the Antarctic continent here, where katabatic winds bring dry subsaturated air descending from the Antarctic continent. And this result notably differs from a previous estimate using an earlier reanalysis product that didn't resolve those winds as well as ERA 5 does. We also find hotspots of snow ablation from non-rain related melt processes in 2 key areas of atmospheric cyclogenesis. And I think that reflects warm air transport. We also find minimal rain related snow melt, as I mentioned. And the model shows that the superimposed ice formed from that melt gets released into the ocean in areas downstream of where that ice was formed, that superimposed ice was formed. And lastly, we find lead trapping of blowing snow, as well as snow released to the ocean upon complete sea ice melt, are both somewhat concentrated along the sea ice edge, albeit with very different magnitudes. And this provides an answer to the question of how much snowfall is blown into leads throughout the winter. Our model finds that about 11% of snowfall is blown into the ocean through leads. So this next figure depicts the average seasonal values, so climatology of the snow mass budget for the entire Antarctic sea ice zone. So on the left are climatological fluxes, starting when the model was initialized February 15th of each year. And on the right are the same fluxes accumulated over time. And this shows how snowfall, despite being fairly continuous year-round, develops this pronounced seasonal cycle that's similar to sea ice extent, because the total mass flux mostly depends on how much catchment area there is to intercept the snow. Whereas snow released to the ocean occurs in this giant pulse that happens over about half of the year. So again, snow is basically acting as a filter, redistributing that snow flux in time and in space. So I think there are 2 main conclusions from the accumulated version of these fluxes on the right. One is that the budget closes to within about 15%. In other words, total snow gain across the sea ice zone is only 15% greater than snow loss in the model. And while this should be around 0%, the 2 should be approximately identical. I find this correspondence remarkable given that the model lacks any explicit constraints that would ensure budget closure apart from the calibration procedure, which, as I mentioned, only uses buoy observations from the Weddell Sea that have basically extrapolated to circumpolar. And the second conclusion is that apart from the rainfall effects, which are small, every process in the model turned out to be significant. So all of these appear to be playing a role, with blowing snow sublimation offering the greatest loss pathway prior to melt. So next up, for the oceanographers in the room, these mass fluxes can be converted into freshwater fluxes using the oceanographic unit of a millisfare drup. And what our model reconstruction gives is 237 millisfare drups of freshwater entering the ocean from snow and rain, known as meteoric freshwater, after those are intercepted by Antarctic sea ice. Now, when I was looking for past estimates to compare with, I found only one, and it's from the data assimilating MIT GCM-based models, SOSI, the Southern Ocean State Estimate, published in the study by Abernathy et al. And this is a model product that many of us use. So I was really surprised to see that the same flux diagnosed in SOSI, which also incorporates reanalysis forcing, is almost half of our estimate at 140 millisfare drips, so about 100 millisfare drips less, which is a pretty big discrepancy. Be happy to discuss this more offline for those curious, but I'll just summarize what I interpret as happening is that SOSI is likely has biases in sea ice formation processes, and it's probably compensating for those biases in order to match salinity observations from largely from Argo floats by artificially reducing the amount of precipitation forcing that happens in the form of snow here. And this fits with what we know about SOSI, that it has sea ice that's about 20 to 40 centimeters too thick in the Weddell and Ross gyres. And as Yoshihiro pointed out in a great intercomparison paper last year, SOSI seems to form too much sea ice near the continent, and therefore melts too much sea ice after that ice gets transported northward. So in any case, I would say this represents, I think, an upward revision of our understanding of how much snow gets transferred from Antarctic sea ice into the ocean. And then the last thing to mention here is that our model reconstruction of meteoric freshwater fluxes, primarily from snow, is equivalent to about half of the, or over half of the freshwater fluxes from sea ice melt that happen each year. And this was diagnosed in Francois' data assimilating NEMO limb run, adjusted by Alex Hauman using ice thickness from ISAT-1 and ship-based observations. So I think overall what I'd argue is that snow on Antarctic sea ice is this huge flux that really deserves, if not co-equal status with sea ice, at least a higher profile when we're thinking about freshwater fluxes and also, water mass transformation. And here I'm thinking about Lily's comment on Francois' presentation yesterday about how the polar front position is set in part by sea ice freshwater fluxes. That's one example where, in this case, snow would be contributing about 1/3 of those fluxes. So my second to last slide for this project represents the mapped reconstruction of snow accumulation from the model for spring and then summer months here. And I'm comparing this result with an existing satellite retrieval snow depth from Cryosat-2. And there's a big difference between the two, as shown when you subtract the fields at the bottom. But I want to emphasize that this difference was actually exactly what I expected and hoped for. And to explain that, I want to talk about this example of temperature data from an ice mass balance buoy in the Amundsen Sea. It's plotted as time versus depth, and that horizontal dashed line represents the ocean surface here. So what this illustrates is this typical Antarctic situation of so much snow accumulating on sea ice that the combined ice-snow column gets pushed downwards in the water from isostatic adjustment. That some of that snow becomes flooded, it freezes, converting into what's known as snow ice. And so a satellite radar altimeter like Cryosat-2, whose pulses are mostly reflected from that boundary between snow and ice, will see snow depth. While my model, which doesn't have any knowledge of sea ice thickness and therefore can't simulate snow ice formation, will only see snow accumulation, the total snow accumulation, which is going to be larger than snow depth. So what appears to be, a discrepancy at first glance between these two metrics, I think actually offers us an estimate of that snow ice formation, which I find to be around 20 to 30 centimeters annually, pretty widespread around the Antarctic continent. And that translates to about 49 to 60% of all snow that gets deposited. And that's a range that's pretty similar to ice cores from the Ross and Amundsen sectors. And then to tie everything together, In another chapter of my dissertation, I use a salinity budget approach applied to Argo float observations to estimate ice production around the Antarctic continent, and I get around 1 meter of ice production. That means that about 20 to 33% of ice production is due to flooding and that snow to ice conversion, rather than basal thermodynamic ice growth. And I think that's a neat new constraint to emerge out of those two separate efforts from my PhD, combined with each other. I'd be happy to talk about that project offline too. And then lastly, I think something that might be of interest to folks here, I've taken a look at trends in the snow model reconstruction over winter and spring. So this is June to November from 2003 to 2025. And of course, sea ice concentration shows, this is not my models, it's just NSIDC, shows these significant declines over much of the Southern Ocean. Significance here is indicated with stippling. It's driven largely by the drops in recent years. There are some exceptions, the Amundsen Sea, this area off of Wilkes Land. But in comparison, the snow model shows weaker trends in snow thinning, but they closely mirror the patterns in sea ice loss. They're focused in the northern Weddell Sea, focused in this area west of the Ross, and those are the areas that have seen the most amounts of sea ice loss. And based on the correspondence with reductions in new snowfall onto sea ice over here, in addition to trends in the snow budget terms, which I haven't shown here, what this suggests is that reduced sea ice persistence associated with later freeze, earlier melt, and simply a smaller ice-covered area in recent years has limited the accumulation of snow along those drift trajectories of sea ice flows. I will note, though, as a circumpolar average, the linear trend in snow accumulation, circumpolar, is not statistically significant. And it shows quite a bit of interannual variability, unlike the linear trend in sea ice concentration. So there are some differences there. But overall, I'd summarize that there's a close alignment between recent changes in sea ice and snow accumulation. And what this suggests to me is that if Antarctic sea ice continues on this new lower trajectory, snow can probably be expected to follow suit. And I'll conclude by first mentioning this work will be submitted imminently, which I've been saying for a while now, but really will be. But the snow product, including the daily model output, will be available for anyone interested in using it. I should mention this work was supported by the ONR through the NDSEG program and also an NSF-OPP postdoc fellowship now. And I'll really conclude by sharing a few open questions that I think our community would benefit from thinking about. So one is, what snow processes are most important to incorporate into ESMs, right? And what observational data will we have to use in order to validate those? I think right now, observations may be the limiting factor in that. How is the loss of snow to leads affected by lead spacing, orientation, and width? My parameterization doesn't include any of those factors. Does snow trapped into leads actually melt into the ocean, or does it just refreeze in the lead and sort of close up that lead? There's sort of a debate in the literature about that. Does brine rejection from snow ice formation activate these ocean ice feedbacks that occur as that brine rejection leads to convective mixing, upward heat fluxes? And could that lead to this sort of conveyor belt that's been suggested where ice grows from the top and then melts from the bottom, sort of cycling downwards? And then in the Antarctic, because this has, I think, been constrained in the Arctic, but for the Antarctic, how much snowfall is delivered by cyclones? And in both hemispheres, how do processes that happen with cyclones, like blowing snow, influence the net effect of those cyclones? And then in bold here, of course, how can we expect snowfall in both hemispheres to be changing in a warming climate, and how is that going to affect sea ice? With that, I'll take any questions.
Thank you so much, Ethan. We have a few minutes for questions, as always. Alex?
All right. Thanks, Ethan. Great talk. This is Alex Rolla, Georgia Tech. So actually, your last question kind of sort of anticipated my question, which is atmospheric rivers. There's been a lot of work done in the last few years on the outsized role that atmospheric rivers play in delivering moisture to the ice sheet. And I'm wondering, now the main difference I suppose would be orography, sort of, but do you think that they are playing also important role in basically putting snow on sea ice in the southern hemisphere.
Yeah, that's a great question. It sort of intersects with the cyclone aspect of this too. I think absolutely, and I can't recall a study examining this for Antarctic sea ice. I think that it would be interesting, especially since cyclones may result in, I think, a less of a net influence on snow accumulation. They might simultaneously be dropping a bunch of snow, but then also that snow gets sublimated as it gets blown away. While atmospheric rivers may have a more positive influence. I think it'd be interesting to look at. And my postdoc involves a lot of cyclone tracking, and it'd be interesting to extend that to atmospheric rivers, I think. Yeah. Thanks.
Thanks, Ethan. That was great.
Yes, sir.
I have a couple of sort of technical questions. They're simple. Towards the end, you concluded numbers of about 200 meter Sverdrups, I think is what the unit is that right? For the melting snow, and then 400 for the sea ice, but then you also said 1/3 of that sea ice is actually refrozen snow. So are those totally separate, or does that 400 include part of the 200?
Yeah, so this 237 here comes from this snow release into the ocean. So it includes, so I think about half of that is going to be snow ice. Yeah. So I guess maybe a more accurate way to put this would be stuff that was at one point snow.
Right.
Yeah.
So about half of that 400 of the sea ice melts.
About half of the 400
so
is.
What I'm confused by is if I want to just know the total freshwater flux.
Oh, gotcha. Sorry, this is a
400
distinct.
to 200, but I think I can't do that because those are not independent, right?
So the freshwater flux from. Yeah, anything about the accounting here? I think this is independent. No, this might include snow ice. Yeah.
Okay. I mean, it's sort of a trivial point at one level, but I was just curious about it.
That's a good point.
So then I have two more questions. One is, I'm curious if you happen to know in those same units what the freshwater flux from melting land ice is.
Yeah.
Because I don't. I always think of it in gigatons.
At least in SOCI, it's about a third of that that they say is snow, or maybe less if the snow term is higher. Yeah.
Yeah. So it's interesting. There's a lot of attention in the glaciology community, in the climate community, to like what's happening to the climate system from melting glaciers. But the fluxes from sea ice, and especially from snow on ice, which is basically precipitation, which is changing, right? They're comparable in magnitude, which I just think is an interesting point to appreciate.
Yeah, certainly. And although I would say to the benefit of glacial melt, it is concentrated in a very narrow range of density classes and area, so it's have a bigger impact.
There's also literature on how far the icebergs travel before they melt, et cetera. So I think it's important for us as a community to realize both these things are contributing to the freshwater flux. Okay, last super simple question. On the compaction physics that you use, did you use empirical models or previous work that had figured out how this works, or is this your own developed?
Yeah, I think I went back to Kojima 1967, so really back to the basics, and it's a simple parameterization. It includes a compactive viscosity, which ends up being the tuning parameter that goes into the model in an inverse sense. So I think that includes, I guess it sort of encompasses all the metamorphic processes like grain sintering and rounding and all of it. Yeah.
Cool. Thanks. Really great talk.
Question. So if I try to simulate snowfall in polar region in both poles, which observation product I should use to evaluate? ERA5, do you think the ERA5 is good, or Merit? Have you checked the Merit too, or have to using the cited data? So this is how good is ERA5? So there's been one, I think,
one evaluation in a circumpolar sense. There have been others that look more locally. Comparing it in this case with CloudSat, it's pretty good. So the various reanalysis products, including Mera, tend to give the same mean picture, but there's a lot of divergence when you look at interannual variability that I think is about a quarter of the total magnitude. So there's certainly a lot of uncertainty there. But I think in a mean sense, it seems to reproduce what we see in CloudSat pretty well. I think ERA 5 was the best out of those evaluated in this study, but I can't quite recall. Yeah. And which is a big motivation for trying to calibrate the model.
Great talk, Ethan. I was curious, looking at CMIP6, like how these processes are represented now. Obviously, incorporating the work you have done into it would be a huge improvement. But I'm thinking about the survey of climatological sea ice that I think Letty Roach and colleagues did a few years ago, just showing that the mean state is all over the place, and a lot of CMIP models have a really unrealistic seasonal cycle. And I'm curious if you have an intuition of like how the representation of snow on sea ice might contribute to that intermodal spread, and if that could potentially be solved by improving this representation.
Yeah, that's a great question. That's something that I hope to look at more. In most CMIP6 models, a handful of these processes are represented. Surface sublimation, and I think density compaction perhaps in some, but there's no blowing snow generally, and often density is prescribed rather than prognostic, so that's a big issue. Melt processes are parameterized. This is not a full thermodynamic snow model that includes mushy physics. I think I would be surprised. What I would expect in a lot of these models is that they probably accumulate too much snow because there's too little loss happening. But at the same time, I think I've seen in one paper, perhaps Marika could offer more insight into this, but I don't think there's a huge positive bias. So that, for me, doesn't make a lot of sense. I think I need to look more at that.
I have a question. I'm a bit confused if we could go back to those like 200 millisfeld or something like that. So it's not about the number. It's more like essentially snow, it is a precipitation. And snow on sea ice, it's just sort of a reservoir where it sits before it gets into the ocean once again. So it's not an extra fresh water, it's just a delayed release, right? So I guess how does it compare with your P minus E in that regard, like precipitation around specifically Southern Ocean, because sea ice is mostly like annual, not multi-annual sea ice. And the other question, or rather my question is, what is that delay, or what is that residence time on sea ice that kind of delays the release of that fresh water into the ocean?
Yeah, that's a great question. I think that speaks to what I was referring to as like a spatial temporal filter. So the delay in the Antarctic, most sea ice is seasonal. So it's mostly in the western Weddell Sea where there's perennial ice that snow might survive for multiple seasons. So that delay in most cases is not going to be more than 1 year. And then in terms of the spatial component, there's generally a northward flux away from the continent of sea ice. So you're redistributing that precipitation back towards density classes of subantarctic mode water, for example, that's going to influence those rather than directly upwell TDW.
And what about the Arctic Ocean?
What about the Arctic? You're going to have to ask someone else that one. Yeah, I've not worked much with the Arctic. Yeah, that's a good question. Thanks.
Okay, last question.
Yeah, so it's a follow-up to Ola's question. So at this point about it's a reservoir, but it's also a reservoir that's moving the snow from one density class to another, I think is really important. So one of the last slides where you were showing the correlation between the changes in sea ice and the changes of snow accumulation.
Yeah.
Because that's happening at the margins, do you think that actually impacts the freshwater flux into the surface ocean? Because that snow would have fallen in regions that are very close to where that ice is going to melt anyhow.
Mm-hmm. You're talking about the correlation between...
Yeah, so on the left-hand side, we've been talking about this reduction in sea ice concentration.
Yeah.
And so you also see a reduction in accumulated snow depth, which you said, I've just lost my area for the snow to fall upon. Mm-hmm. But now that snow is falling directly into the surface ocean, which is likely where that ice would have melted, and the accumulated snow would have melted into the surface ocean as well.
Yeah, potentially there's not a huge impact from that.
So it would be nice to have an additional panel here, which is actually showing the change in the surface freshwater flux.
Yes, yeah, I have that, but only for surface freshwater flux associated with sea ice, and not the open ocean component, which I've sort of deemed out of scope here. I think I would say there's also, it's not just a northward drift, but also a west to east drift. So there's that other component that gets lost when sea ice contracts.
Yeah.
Which could have implications.
Yeah, so that's right, because part of this will be the effective part as well, and separating out those components would be really nice. Yeah. Thanks, Ethan.
Cool, thanks.
All right, thank you so much, Ethan and Xianghong, for your talks this morning.